Welcome to a captivating journey into the world of sound and light. Today, we will dive deep into how these fascinating aspects of science travel through different mediums. We will unravel the properties of waves and energy, exploring concepts like vibrations, frequency, and even the mesmerizing play of light. Buckle up as we embark on this interactive lesson, designed to pique your curiosity and deepen your understanding of the scientific principles governing sound and light. Let's start with sound. Sound is a vibration that demands a medium, be it a solid, liquid, or gas, to travel. This means that sound is classified as a longitudinal wave. It moves through materials by causing particles to oscillate back and forth. So, have you ever wondered how fast sound travels? In air, at room temperature, sound waves cruise along at about 343 meters per second. However, if you think about space, a total vacuum, you would realize sound can't venture into that emptiness because, without particles to vibrate, there's nothing to carry those sound waves. Understanding this principle highlights the very nature of sound and its reliance on a medium for transmission. Now, let's discuss how sound reaches our ears. Sound waves enter through the ear canal and cause the eardrum to vibrate. These vibrations are then conveyed to the cochlea by three small bones known as the hammer, anvil, and stirrup. In essence, it's the cochlea that converts these vibrations into electrical signals destined for the brain. Remarkably, the human hearing range spans from about 20 Hz, which feels almost like a gentle rumble, to 20,000 Hz, or 20 kHz, where we perceive higher frequencies. Next up is the Doppler effect. This phenomenon explains the change in pitch of a sound as the source moves relative to an observer. If a train rushes towards you, the sound it emits suddenly seems higher in pitch. Yet, as it passes, that pitch decreases. This principle is not just limited to trains, it also applies to everything that moves, from vehicles to emergency vehicles. Moving forward, let's turn our attention to light. Unlike sound, light is an electromagnetic wave capable of moving through a vacuum, unfazed by the absence of particles. Light travels at an astonishing speed of about 300,000 kilometers per second, or 186,000 miles per second, in a vacuum. One intriguing aspect of light is its wave-particle duality. It exhibits properties of both waves and particles, specifically photons. Now consider how we perceive light. Often, we talk about reflection when light bounces off surfaces. The law of reflection states that the angle at which light hits a surface equals the angle at which it bounces away. Mirrors, whether they are plane, concave, or convex, utilize this reflection principle. For instance, a plane mirror produces a virtual image that maintains the same size as the object but appears upright and reversed left to right. However, convex mirrors, which are commonly used in cars as side view mirrors, provide a wider field of view. They help drivers spot more of what's happening behind and beside them, which enhances driving safety. Another fascinating property of light is refraction, which refers to the bending of light as it transitions from one medium to another. This bending occurs due to a change in speed as light travels between air and water, for example. The index of refraction quantitatively describes how much light slows down as it enters a different medium. This principle is utilized in lenses that focus light, such as those found in glasses. You may have experienced the bending of a straw in a glass of water. This optical illusion occurs due to refraction, making the straw appear crooked. Moving on to dispersion, this term describes the separation of white light into its various component colors, a beautiful demonstration of transparency and light interaction. A classic example is the rainbow, which exists thanks to dispersion. Sir Isaac Newton was actually the first to demonstrate this fascinating phenomenon using a prism. When white light passes through a prism, it splits into a spectrum of colors referred to as Roygbiv, comprising red, orange, yellow, green, blue, indigo, and violet. Each of these colors corresponds to different wavelengths of light. If you've ever seen a rainbow, you might have noticed that the colors appear in a specific order, with red always on top and violet always on the bottom. Interestingly, indigo is often debated. It can be seen as just a darker shade of blue or violet. Newton originally identified 5 basic colors and later added orange and indigo, aiming for a neat 7 to align with various systems, such as the 7 notes in music or the 7 days of the week. Isn't it astounding how natural phenomena interrelate? On to the electromagnetic spectrum. This expansive range involves all types of electromagnetic radiation, from long wavelength radio waves to the very short gamma rays. Remarkably, visible light, which our eyes can perceive, is just a sliver of this vast spectrum. The type of electromagnetic radiation with the longest wavelength is, in fact, radio waves, playing a vital role in communication, from listening to radio stations to using cell phones. Speaking of our eyes, let's explore how we perceive color. The human eye contains 3 types of cone cells, sensitive to red, green, and blue light. By combining signals from these cone cells, our brains can generate the multitude of colors we see. However, some individuals experience color blindness, usually a deficiency in red-green cones, limiting their ability to distinguish certain colors. Understanding the biology of our vision opens up a world of insight into how humans interpret the colorful world around them. Today, we explored the science of sound and light, delving into how sound travels as a vibration through various mediums and how light moves as an electromagnetic wave. We learned about principles like the Doppler effect and the fascinating phenomena of reflection, refraction, and dispersion. Understanding the properties of sound and light not only enhances our appreciation of the natural world but also enriches our knowledge of physics and biology. From the speed of sound and light to the intricacies of our eyesight, these concepts highlight the brilliance of science in everyday life. Thank you for joining me on this exploration of sound and light. I hope you found this journey enlightening and that it sparked your curiosity about the natural laws that govern our world. Keep questioning, keep exploring, and until next time, stay curious and keep shining like the light we learned about today.